Hello, this is Oğuz, and in this video I will present my graduation project called Computer-Assisted Medical Diagnostic Tool for Medical Ultrasound Images. And the project is supervised by Professor Dr. Uğur BAYSAL. Nowadays, it is proven that breast cancer is the most common cancer among women, and survival rates are vary widely by many factors. Two of the most important factors are the type of cancer and the stage of the cancer at the time of diagnosis. Hence, it is very crucial to detect and classify the cancer at early stages to avoid next phases. Thus, this project presents a software tool to process medical breast ultrasound images by using deep learning methods to provide faster and more accurate detection and classification. For design requirements, the open source data collected at baseline includes 780 breast ultrasound images with an average image size of 500 to 500 pixels and bit depth of 24 bits. The images are categorized into three classes, which are normal, benign, and malignant. The programming language of the software is Python. The Keras framework was applied, and the TensorFlow GPU backstage was called to implement the semantic segmentation, recognition, and training for both neural networks. For solution methodology, project mainly utilized the deep learning algorithm called UNet for the prediction, and modified convolutional neural network for the classifier part. So what is UNet? UNet is a type of convolutional neural network architecture which is developed at Freiburg University Computer Science Department for fast and precise segmentation of the images. It provides better segmentation on biomedical images with small amount of dataset and computational power. So here we can see the small illustration for UNet architecture. Network consists of two parts, the contraction path and the expanding path, and the network's name comes from the U-type shape of the architecture. The model starts with using 3x3 convolution followed by a rectified linear activation function. The important part is that model only uses valid part of the convolution, which means that for every 3x3 convolution process, one pixel border is lost. This allows to process large images into individual channels. And the next operation is the max pooling operation. This operation reduces the XY size of the image, which means a smaller size image. It processes every channel separately and propagates maximum activation from each 2x2 window to the next feature map. And the next operation is the 2x2 upconvolution operation. This 2x2 upconvolution uses a special kernel to map each feature channel to the 2x2 pixel output window, again followed by a rectified linear activation function. After the expanding path reaches the same size as the input image, process stops and output segmentation map has two channels, one for the foreground and one for the background. Due to the unpadded convolutions, this output map is smaller than the input image. For loss calculations, standard binary cross entropy and attenuation can be calculated with DICE, which is a performance criterion frequently used to evaluate performance in biomedical images. DICE loss is based on Sorensen DICE coefficient or Tversky index, which attaches similar importance to false positives and false negatives, and is more immune to the data imbalance issues. For performance calculations, software utilizes IOU approach. IOU means intersection over union. It's a pixel-based metric and is often used when evaluating the segmentation performance. The overlapping pixel ratio between the target matrix and the resulting matrix is taken into consideration. This metric is also associated with the DICE calculations. So here we can see the testing and results of the software. On the left side of the monitor, we can see the original medical image. On the right side of it, we can see the predicted and classified image. On the right side of the monitor, we can see the real medical images with their ground truth images and their predicted images. The ground truth images are the mask images of the breast tumors, and it is provided by the dataset that collected before. For performance evaluation, here's the accuracy report of the software. The project's goal was to reach 80% accuracy, and it is satisfied. In this proposed model, we can detect and classify the cancer with 82% accuracy rate. So here we can see the confusion matrix of the software. Design is tested with the ratio of 0.1, which means total of random 78 images have been used from the dataset that contains 780 images. As a conclusion, experimental results prove that this proposed method is very effective with small amount of dataset and can be further improved to higher accuracy rates by adjusting the neural network and increasing the dataset size. Thank you for watching.